Okay. My topic is the study of the formation of Rho waves in an adiabatic electronegative plasma. My outlines are structured as follows. Now, coming to the introductions. Now, Rho waves are also called freak waves or monster waves, are rare, highly energetic, high amplitude, multiple phase events that carries dramatic impact. Rho waves appear in seemingly unconnected systems, such as in the form of oceanic Rho waves and optical fiber, superfluid helium, stock market crashes, and Bose-Einstein condensates in plasma physics, etc. Figure shows the picture of the mountainous Rho waves spotted in the sea. In the ocean, Rho waves appear suddenly and disappear without any trace. Though the physics behind Rho waves is still unclear, observations indicate that they are stiff, isolated, tightly grouped wave structures. Modulation instability, also called Benjamin-Ferrar instability, is suggested as a possible mechanism for the generation of such energetic localized pulses in many nonlinear dispersive media. Due to modulational instability, wave energy self-focuses into a small isolated wave group, leading to the formation of very high amplitude localized wave pulses. The famous nonlinear Schrodinger equations provide a number of solutions to study the evolution and dynamics of envelope pulses in various systems. In hydrodynamics, Peregrine first formulated the space-time localized solution or rational solutions of the nonlinear Schrodinger equations, which was later recognized as Peregrine soliton in ocean. Peregrine soliton is considered as a prototype of the Rho wave. Okay, now we are all familiar with the polytropic equation of states, which relates the plasma density with temperature or pressures as follows. Here, gamma is the polytropic index or adiabatic index, which is equal to the ratio of the two specific heats measured at constant volume and constant pressure, respectively. Okay, no, for constant pressure and constant volume, it should be. The value of the polytropic index is characteristics of the type of process the plasma experiences. For examples, at gamma is equal 1, it represents the isothermal process, and if gamma is equal 3, it represents an adiabatic process in one dimension. Okay, now electronegative plasma, the rapidly growing interest in the study of electronegative plasma is not only because of its novel applications in the microelectronics and photoelectronic industries, but also its existence in space astrophysical and laboratory experiments. In most of the cases, people used fluid electronegative negative ions as a fluid elements. But a number of theoretical studies have predicted that at low pressure ENPs, it is appropriate to describe negative ions by Maxwellian distributions, which was conclusively verified by Ghim and his colleague through experiment. On the other hand, very recently, Bailung et al. And his group have observed Peregrine soliton experimentally in a multi-component plasma with negative ions. They found Rho wave amplitude equal to thrice the amplitude of the background carrier wave, and their results were agreeable with the rational solution of nonlinear Schrodinger equation. Now, motivations. Our motivations to study Rho waves in adiabatic electronegative plasma is because understanding the origin and the characteristics of Rho waves in diverse areas of physical system has been a topic of continual research for many recent studies. Experimental observations of Peregrine solitons has already been detected in electronegative plasma, and the flexibility of polytropic index motivates one to consider the adiabatic model for plasma hysteresis, which provides a more general and realistic plasma in a variety of environments. Now, let's come to the theoretical model. We have considered an unmagnetized, one-dimensional, collisionless electronegative plasma comprising adiabatic inertialess electrons, adiabatic inertialess negative ions, and the cold mobile positive ions. Now, fluid equations are shown here. This is the continuity equations for R species. R means electron, ion, and negative ion of electron, negative ion, positive ions. And here, this is the fluid equations. And for inertial spaces, we must neglect the right-hand side, and we get these equations. And these are energy flux equations. Now we are interested, we are interested in investigating the nonlinear propagation of low phase speed ionoacoustic waves, whose in the long wavelength regions as compared to ion Debye length. This is the limit for velocities. The phase velocity is very much less than the thermal velocities of electrons and negative ions, and very much greater than the thermal velocity of positive ions. So we are considering, in this limit, we are considering the cold positive ion fluid as the temperature of the positive ions in the fluid equation. We must consider the temperature of positive ions in the fluid equations when this phase velocity is comparable with the thermal velocity of positive ions. But at this limit, the effect of Landau damping will be significant. Now, after some transformations, coordinate transformations and the mathematical calculations, we finally come across with these expressions, these beautiful expressions for positive, inertialess electrons and negative ions. And these expressions can be reduced to the Maxwellian isothermal Boltzmannian form at gamma is equal 1. But we cannot put gamma is equal 1 directly in this equation, then the equation will vanish. First, we have to make the Taylor expansion, then we have to put gamma is equal 1. And finally, we will get the expressions for Boltzmannian form at gamma is equal 1 in the isothermal limit. Okay, now before going to derive the nonlinear Schrodinger equations for our model, we first binomially expand the inertial spaces, the density for inertial spaces up to power 3, and then then substitute them in the Poisson's equations. Then we'll get the coefficients as shown here, A1, A2, A3. Now, following the standard procedure, we introduce the states coordinates, and here Vg is the group velocity, omega and k are the frequency and wave numbers of the carrier waves. Now, following the coordinates are transformed like this. Now, following the standard procedure of reductive perturbation method, or also called multiple scale technique, we finally derive the nonlinear Schrodinger equations. It's shown here. Here, P is the coefficient of dispersions, and Q is the coefficient of nonlinearity. These are the expressions. The coefficients in a nonlinear terms are expressed in terms of the fundamentals variables A1, A2. Okay, shown here. Now we get the space-time localized solutions from the Schrodinger equations like this. This represents Rogge solutions where a huge amount of energy is concentrated into relatively small spatial regions predicted by the solution. Now, considering small amplitude modulation, small amplitude modulated perturbations, we have derived the nonlinear dispersion relations for modulated waves here. From this expression, it is clear that when PQ is less than 0, omega is real, and amplitude modulated envelope is stable against external perturbation. If PQ greater than 0, then omega is imaginary, and amplitude modulated envelope is unstable against external perturbation. And in this case, there may be bright envelope solitons, there will get bright envelope solitons, or the modulated waves, the carrier waves may collapse due to random external perturbations. For the present study, we investigated special modulated unstable solutions localized in space and time, which is typical for raw waves at PQ greater than 0. Now, coming to the results, we have drawn the contours for PQ is equal 0 to investigate the regions for stable and unstable pulses. In the blue colored regions, the waves are modulationally unstable, and here they are stable. Now, wave number threshold or critical wave numbers at which modulational instability sets in is represented by this line. This line along this.
Kakoti, you have 2 minutes more.
Okay, thank you, sir. And now, from the variation of critical wave number with adiabaticity or polytropic index, it is shown that it is found that the wave number, the critical wave number, increases with increase of gamma. This represents, here we can conclude here that the possibility of formation of ROG waves decreases with increase of polytropic index, with increase of adiabaticity. As we are interested in the lower wavelength limit, in this limit, ion acoustic. Okay, the effect of negative electron to negative ion temperature ratio on the modulation instability is shown here. With increase of temperature ratio of electron to negative ion, the case is shifted more to the higher values. Similarly, the effect of density fractions on Kc is shown here. For entire range of gamma, Kc is shifted to higher values with increase of density fraction of negative ions. Well, for numerical, we have considered the numerical parameters based on him and his colleagues' experiment, where they observed an electronegative pore and an electropositive halo in his experiment in the ion acoustic limit. Now, coming to the ROG wave amplitude, we have here drawn the maximum ROG wave amplitude contour plots against the wave number and adiabaticity. Here, the lighter color regions correspond to high amplitudes. Okay, now if we move from here in this direction from left to right, then the amplitude of ROG waves increases, which represents that with increase of adiabaticity, the nonlinearity increases, which makes the wave amplitude taller. Now here are the conclusions, and these are the references. Thank you for all the listeners for giving your valuable time, and I want to
thank you very much,
supervisor, for his advice. Okay.
Yeah, thank you very much. Is there any question?
PK Karmakar, you can ask the question. Dr. PK Karmakar.
Yes. Am I audible?
Yes,
Yes.
you are audible.
Yeah. So, okay, I am interested to know what decides the exponent of epsilon in the stress coordinate system you have adopted. Somewhere it is half integral, somewhere it is integral.
Sir, what? I'm kidding, sir.
Now, what decides the exponent of epsilon appearing in your stress coordinate system?
Epsilon.
Yeah, epsilon.
Sir, epsilon is a small parameter.
No. Fine. No. What decides its exponent? Power.
Power.
Yeah.
Sir,
in normal KdV equation derivation, the stress coordinates adopted was for position epsilon appears as epsilon to the power half, and in the time it was what? Epsilon to the power 3/2. And in some other cases,
We'll call Mr. N.A. El Safei from CSRA, Damietta University, Egypt. And is he there?
Yes. Hello, sir.
Okay. Thank you.
Please on your
Shona?
Nora, please on your video.
Oh, Shona.
Topic of is her presentation, oral presentation is three-dimensional ROG waves in DF regions of Earth's atmosphere with hybrid kaons, Thales distributed electrons and positrons. So I will ask Mr. Safai to start his presentation.
Yes, sir.
Yeah, please start.
Yes. Hello, everybody. My name is Noura Ahmed. Hello.
Yes,
My name is
you're
Noura
audible.
Ahmed Al-Shafai. I am from Egypt. I am a master's student in Faculty of Science at Zenat University. I will present our work that has a title, Three-Dimensional Rogue Wave in the Region of Earth's Ionosphere with hybrid kernels, size distributed electron and positron. Supervisors Prof. صلاح كامل اللبني and Prof. وائل فاروق الطيباني, Professor of Theoretical Physics, Physics Department, Faculty of Science, دمياط University, and Prof. Nabila Ahmed Al-Badwi, Professor of Applied Mathematics, Math Department, Faculty of Science, دمياط University. Outline of our work: introduction, govern equation and derivation of 3D nonlinear Schrödinger equation, manipulation and stability of ion acoustic wave, ion acoustic log wave solution, and discussion, acknowledgement, and reference. First,
Excuse me. Professor Bose, is there any problem? I think. Professor
Hello.
Bose.
Yes.
I think, is there any problem from the speaker side?
Sound, yes.
So I
Sound, there
think,
is a problem. We cannot hear properly.
okay, so I think we should call to next speaker.
Yes.
Let me resolve this issue. I contact to the speaker Nora. So you can
Yeah, you
invite
can
the
contact directly.
Yeah,
to
I
the
am
person.
contacted. You ask the other
Okay,
speaker.
thank you. Thank you. So I will call Mr. Basnet, S. Basnet from Tribhuvan University, Kathmandu, Nepal. Are you here?
Yeah, yes, sir. Yes, sir. Yes, sir.
Oh, can you present your
Hello.
paper right now,
Okay,
oral
yes, sir.
presentation?
Yes, sir.
hello.
So you are going to present this collisional two ion species plasma with bimaxwellian electrons and Bohm condition.
Just
Okay.
minute. Just
Hello,
minute.
sir.
Nora, Nora.
Yes, sir.
There was some
I'm
problem.
so sorry. Yes. I'm so sorry. There is a problem in network.
Yeah. And you please, hello, Nora.
Hello, sir.
Yeah,
Yes.
please start and finish your talk in within time. Okay.
Or if not possible right now, we can consider
Next.
her later on.
Hmm.
Okay, after 15 minutes or after 20 minutes, we can
Okay,
consider.
Nora, you present after this talk. Okay.
Okay, sir. Okay.
Okay. Okay, Mr. Basnet.
Okay, thank you,
Please
sir.
carry
Thank
on.
you.
Okay.
Thank you, Professor Bose. Is it sharing, sir?
Yeah. We can see.
Okay. Thank you, Professor. Good afternoon, and namaskar to all. I am Suresh Basnet from Central Department of Physics, Tribhuvan University. I am a PhD student. So today I'm going to present my work, collisional two ion species plasma with bimaxillary electrons, and there is the modification of the bomb seed condition in the presence of the electron impact ionization and collision process. This is my outline of the presentation. So basically, for multi-component plasma consists of the more than two species of positive or sometimes negative ions. And for collisional plasma, the plasma satisfies this condition that the electron dipole length is smaller than the ion neutral collision mean free path and very smaller than the dimension system. And in the presence of the if there is no collisions, for the cold ions, the bomb seed condition gets modified for the two ion species plasma. This is given by the Riemann in 1995. Here the subscript not represents the parameters at the seed edge, and the CS1 and CS2 is the acoustic speed for the ion species at the ion species. So here there are two unknowns. Here the first is the velocity of the lighter ions and the velocity of the heavier ions. So we need the constant to determine the speed of each ion species at the seed boundary. So when we apply the constant, then it gives there are the two possible solutions. That means the first solution is each ion species can reach the seed boundary with the individual acoustic speed. And then second possibility is they can reach the seed boundary with the common speed, and this is given by this Balod and Hagen in 2011. It is experimental as well as theoretical work. So applications of plasma. So in most all when the plasma comes in contact with the metal surface, the plasma wall interaction is ubiquitous features of the bounded plasma. So the study of this plasma wall interaction is more important due to its wide sense of the Goering applications, and one of the important applications in the diverter part of the fusion devices. And next one is the sputtering process, and the next one is the etching. Besides this, there are other important applications of the multi-component plasma to produce the neutral beam in the fusion plasma. So the understanding of this multi-component plasma seed and pre-seed structures helps to it's very crucial. It is very important to understand the instability occurs in various astrophysical and ionospheric plasma phenomena. Motivation: in most of the discharges, plasma consists of the two ions. Then when the plasma comes in contact, there's one question, then what happens? So when plasma hits the metal surface, there are different possibilities occurs. Sometimes particles may be reflected, and sometimes it causes the secondary electron emission from the wall. Sometimes the particles are trapped by the wall. So there are different mechanisms occur in the plasma wall when the plasma hits the metal surface. This is our proposed model to study the collision multiple ion plasma. Here, this is the core plasma part, and here is the wall. There are the two ion species plasma, and this one this represents for the heavier ion, that is the helium ions. Argon ions, and this is for the helium ions. Here we're going to study the plasma seed parameters in this region, the pre-seed as well as seed region. These are the governing equations. This is the distribution functions for bimaxillary electron distribution. Here, first term represents the cold electron part, and this is for the hot electron part. Here, delta E represents the volumetric composition of the bimaxillary electrons, and this is the estimation of the effective temperature of the two temperature groups of the electrons. Here, beta represents the temperature ratio of the cold to hot electrons. And this is the steady state continuity equation. This is for the momentum transport equation. Here we take the collision force is given by this relation, and collision frequency is velocity dependent. But before this previous work, there are so many works in the collision of plasma in multiple ion phases. They take the collision frequency is constant collision frequency, but I take here the collision frequency is velocity dependent. This is the Maxwell equation to find out the potential variation in the transition region, and this is the generalized bomb seed condition. When we put this value in this relation, we get this relation. Here, this is the term appearing from the collisional part, and this is appearing from the electron impact ionization process, and this is the common speed predicted by the previous work. So what we found that here the velocity acquired at the seed boundary, that is the quadratic form, and it has obviously two roots, and this first roots where A is the positive value, B is also positive value, and C is negative value. When you put this relation in the first rod, they will gives the negative velocity, which is discarded according to our considered geometry. But this we want to take this relation. This is the Bohm-Schmidt condition, the modification due to the electron impact ionization as well as collision term, velocity dependent collision term. And if there is no collisions and no electron impact ionization process, this previous relation, this one relation is converted in the previous work, that is Weyl agreement with the previous work. These are the input and boundary parameters. These are all taken from the previous experimental work from Sevan et al. 2003. Electron density and temperature are similar to the previous work, and this is the length of region of interest is also similar to the that is in the range of the previous experimental work. So results and discussion. And this is the now I am going to discuss the effect of bimaxonal electrons. Here delta E represents the volumetric composition of the bimaxonal electrons. So what we found that when we increase the concentration of the hot electrons, the peak in the space charge densities appear. Here in the precede region, the space charge density almost zero. That means there is small fluctuating nature is appeared in the precede part, at the initiation part, but the space charge density is almost zero. But when it enters when we enter the C3 region, the space charge density is sharply increases and obtain its maximum value. Then after it also decreases. Similar phenomena, this is for similar to the all cases of increasing the concentration of hot electrons. And this space charge density helps to estimate the thickness of the C3 region. So thickness of the C3 region is given by this relation, and we found that in our case, the thickness of the C3 region is widens from 1.09 millimeter to 5.8 millimeter. This is the gradient of the electric potential in variation in the C3 region. So electric field is very weak in the precede part. Once in the seed part, the electric field is more strong, and we calculate the electric field at the seed boundary. We can get from our curve we can get the value of the electric field at the seed boundary 0.63. It is normalized value, but we can predict the electric field at the seed boundary from the previous Riemann's work. And this by using this relation for the collisional plasma, we get this value 1.31. This is almost our calculated value is just half of the previous Riemann's theory value. This is the velocity profile of the. This is for this first part is for the helium ions, and this is for the argon ions for the various volumetric composition of the bimaxonal electrons. This is the predicted Franklin speed of the lighter, heavier, helium ions, and this is the previously collisionless plasma for the collisionless plasma. But when we include our velocity dependent collision term, the velocity is reduced. The velocity of the common speed of the positive ions reduced, and the value is 0.87. That means the value is reduced by the 13% in terms of magnitude. This is for the same for the argon ions. This is the Franklin predicted speed for the collisional plasma, and this is for the collisionless plasma. In both cases, the velocity increases towards the target surface, but increasing rate is higher for the helium ions, and the velocity is also increasing with the increasing the volumetric composition of the hot electrons. This is the, okay, sir. Thank you, sir. This is the particle density profile, this also gives the idea of the idea of the C3 region. So in the precede region, the particle density almost equal, but once it enters the C3 region, the electron density decreases sharply, and this minimum point the minimum is occur in the wall, but this minimum point is shifted with increasing the concentration of the hot electrons towards the precede part. This is the now I'm going to discuss the ion neutral drag force. So this is the alpha 1 represents the ion neutral collision strength of collision for the helium, and this is for the argon. Alpha 2 represents for the argon. So what we found that the alpha 2 has more significant effect on than the alpha 1. This is due to the large collision cross section of the argon ions. This is the collisionless plasma, and this is the Franklin speed, and this is also the collisionless plasma, and this is the Franklin speed for the collision plasma. So what we found that when you increase the collision, the velocity of the helium ions goes behind the individual acoustic speed. But it does not it does not goes behind this collisionless plasma. So in this case also, the individual acoustic speed is less than the common speed of the common speed. When we increase the collision, it does not again goes to the individual predicted by the Franklin speed. So this is the comparative study of the energy of the ions. We can clearly see that the energy of ions decreases in the presence of the collision, and this is the effect of the ionization, electron impact ionization. Electron impact ionization. So when we increase the electron impact ionization, the potential is sharply increases in the sheath region, but it has no significant effect in the pre-sheath part. These are my conclusions. These are my references. I'm thankful to all persons, and I'm also thankful to the Dr. Prajapati sir for giving this opportunity to present my work. Thank you, sir.
You can call Professor Bose.
Yeah.
You can call Shivam Gupta first.
Gupta,
Nora is present. Nora.
Yeah.
Yes, sir.
Okay. So start your presentation.
We'll start with Nora's presentation. Okay.
Okay, sir.
Okay, please start.
Introduction.
Yeah, you are audible.
Plasma definition. Plasma is a first state of matter, or a plasma is a quasi-neutral gas of charged and neutral particles which exhibit a collective behavior. Electronegative plasma, plasma comprising both positive and negative ion, which exist in astrophysics, in Earth's ionosphere in D and F regions through H plus and H minus plasma, or H plus O2 minus plasma, and in laboratory experimental through argon or fluor plasma. Ion acoustic wave is a one of type longitudinal oscillation of the ion and electron electrons in plasma, much like acoustic waves traveling in neutral gases. Rogue waves, also known as scalar wave, Gantt wave, or relative wave, is a singular or rare, short-lived and higher energy event and very high amplitude. Govern equation and derivation of 3D nonlinear Schrodinger equation. We have two fluid equation for positive and negative ion. Firstly, for positive ion, we have a continuity equation which represented the conservation of number of density, and we have equation of motion represented the conservation of momentum equation. We have magnetic field term and electric field term. For negative ion, we have continuity and momentum equation also. Finally, we have Poisson equation, which have 4 component plasma, electron density, proton density, and positive and negative density. Cyclotron frequency is defined in this form, and gamma is mass ratio, and beta 1 and beta 2 are defined as in this form. The hybrid Kern's distributed electron and positron are defined in this form. We note that if we take Q goes to 1, we goes to non-extensive density, and if we have alpha equal 0, we have non-extensive electron density and positron. The normalized electron and positron number density in general form will take this form, which alpha 1 and alpha 2 and alpha 3 will take this form. Then the Poisson equation will take this form, general form in this form. So To derive the 3D nonlinear Schrodinger equation, we employ the derivative expansion method, which have a stretching in this form and the dependent variable in this form. We have in the direction x and y and z, you have in x and y and z epsilon. Epsilon is n minus 1 because the electric field in the direction z have effect only in direction x, z and y and z. Using the expression equation from 6 to 8 into equation 1 to 5 and collect terms obtain epsilon, we have the first order of epsilon in this form and the linear group linear dispersion relation and the group velocity in this form. For n equal 3 and L equal 1, we obtain the 3D nonlinear Schrodinger equation in this form. Modulation and stability of ion acoustic wave. If we consider the wave, the plane wave solitary solution in this form, and using this solution in 3D nonlinear Schrodinger equation, we obtain the nonlinear dispersion relation for modulated ion acoustic wave can be written in this form, and critical wave number in this form and the modulation condition may be occur if we have one of the following two conditions satisfied. This point will be showed in the figures. Ion acoustic Rho wave solution will take the first order Rho wave solution in form and second order Rho wave solution in this form. Result and discussion. Firstly, the effect of non-thermal parameter when increase the effect the non-thermal parameter alpha NE alpha equal 0.05 and NB alpha equal 0.25. NE we have two multi-region of stability and instability for theta equal theta critical. Theta is the modulation obliqueness theta. We have for theta greater than theta critical, we have BQ less than 0 is a stable region, and for BQ less than 0 for theta less than theta critical, we have unstable region. For theta for omega equal omega cyclotron frequency, we have BQ region of BQ less than 0 unstable. For omega equal omega critical, we have for omega less than omega critical, we have stable region. For BQ equal greater than 0, and for B NB we have alpha equal 0.25. We know that the unstable region increase and instability and stability decrease. This means that the alpha gives the system more energy and making the system more unstable than in region which BQ less than 0, and decrease this region for BQ greater than 0. The effect of Q non-extensive parameter, the increasing non-extensive parameter in E and B. For E, we have 0.72, and in B, we have 0.85. For E, we know that E and B, we know that the unstable region decrease and the stable region increase. In this form, we know that the increasing non-extensive parameter increase the stability of the system. The effect of the physical parameter alpha and Q and omega CD cyclotron frequency and sigma temperature ratio. Sigma, this is the temperature ratio of T positron to T electron on the Rho wave solution. For A, we have the variation of the increasing of non-thermal parameter increase the instability of the system, which increase the width and the amplitude of the Rho wave, and for increasing non-thermal Q non-extensive parameter, decrease the amplitude and the width of the rock wave, and increase the stability of the system. Also, for second order rock wave solution, the same effect can be exist. For first variation, for omega equal 0.2 and Q equal 0.65, we have the variation of temperature ratio and the variation of cyclotron frequency. For increasing the temperature ratio, the width and amplitude decrease. Also, for increasing the cyclotron frequency, the width and the amplitude will be decreased.
Okay, you have 2 minutes more,
Okay.
Ms.
The
Nora.
3D plot for first and second order solution, we know that the second order solution have a very higher energy than the in the amplitude and width than the first order amplitude. This attributed to be the fact that the second order solution has extra poles which accumulate extra energy on the instability. Finally, we have a comparison between first and second order rock wave solution for hybrid Kern-Thales distributed electron and for Maxwellian electron. We know that for hybrid distributed electron and positron, very high, the amplitude is very higher than the amplitude obtained by Maxwellian distribution. This means that Maxwellian distribution is not correct for all higher energetic particle. Acknowledgement. I would like to express my deep thanks to Prof. Rifat Sabri for helping me to accomplish the numerical codes. Reference. Thank you.
Okay, thank you very much, Ms. Nora. Is there any question?
Yeah, I want to ask one question. May I?
Yes, sure.
Yeah, I want to ask one question. Okay, there are so many non-thermal distributions, right? Like your non-extensive Q distribution and Kappa distribution. Why have you considered this hybrid class of distribution function comprising of your Thales distribution, and on the other hand, another part is your Keynes distribution? Why? Can you justify a little bit?
Yes. Please,
can you justify your distribution function for the thermal species?
Sir, please repeat.
Can you justify your choice about the distribution function in your model?
Yes, distribution function to prove electron and positron distribution.
No, there are already so many non-thermal distributions, right? From thermostatistical point of view, there are so many non-thermal distributions like Kappa distribution, Q non-extensive distribution, etc., etc. But you have considered the hybrid type of distribution function comprising of your Keynes distribution as well as your another part is another. Okay, so Thales distribution. So can you justify this point?
For hybrid distribution function, sir?
Yeah.
Yes, I can. I have it, but the time.
Okay.
Sorry,
I think
Dr. Karmakar, what you do, you put your question in chat box so that Nora will answer you. Okay.
Okay.
Yes,
Okay.
it will be nice.
Okay. Yeah.
Okay, then thank you again to Nora El-Safei. And now I will call Mr. Shivam Gupta. Shivam Gupta, are you here?
Yes, sir. Yes, sir. Am I
Yeah.
audible, sir?
Please prepare your presentation.
Okay, sir. Thank you, sir.
Share
And
with
keep
us.
your video on. Okay.
Okay, sir.
Okay, thank you. Yeah, Mr. Shivam Gupta from IIT Indian Institute of Technology, Roorkee. And he will present today, his oral presentation is on study of electron impact fine structure excitation of Kr plus ion. Okay, please,
Okay, sir.
Mr. Gupta.
Good afternoon, everyone. I'm Shivam Gupta from IIT Roorkee. First, I would like to thank the organizers for giving me opportunity to present my work here. So today I will discuss my recent research work on electron impact fine structure excitation of krypton plus ion. This is the outline of my talk. The main objective of this work is to perform the calculation for electron impact excitation of singly ionized krypton plus ion. This work is important because in many spectral measurement of different krypton plasma, eminent emission lines of krypton plus ion are originating along with the emission lines of neutral krypton atom. So far, the characterization of such krypton plasma is performed through the detailed collisional radiative model using the emission lines of neutral krypton only. One can, however, for the characterization of the same krypton plasma, one can use the krypton plus line also, but due to the lack of electron impact excitation calculation of krypton plus ion, detailed or suitable collisional radiative model is not developed for the characterization of the krypton plus plasma. So here our first aim is to perform the calculation for large number of fine structure transitions from the ground state of the krypton plus. From the literature, we find that an extensive attention has been paid on different experimental and theoretical methods to calculate the electron excitation cross sections of the neutral atom only, and very few experimental studies have been performed for the electron excitation cross sections because of inherent difficulty to perform the experiment. Therefore, there is an urgent need of accurate theoretical calculation of electron. What?
Hello, please mute all the participants.
Okay. So therefore there is a urgent need of accurate theoretical calculations of electron ion cross sections. Recently, Dipti and Srivastava et al. Srivastava have performed the detailed relativistic distorted wave calculation for argon plus ion, where they calculated the electron impact excitation cross sections for large number of transitions, and further they use these transitions. Further, they use these excitation cross sections in the development of collisional radiative model for the diagnostic of surface streamer plasma through the emission lines of argon and argon plus ion. Very recently we did the detailed relativistic distorted wave calculation for xenon plus ion, and in addition Wang et al. Also performed the EI calculation for fine structure excited states using the Dirac B-spline R matrix method, and using the calculated cross section they further developed the collisional radiative model. From these studies, we find that due to the lack of electron impact excitation cross-section data of singly ionized inert gases, only few collisional radiative models are developed for the inert gas ions. So therefore we did the calculation for krypton plus ion, and these cross-sections are directly used any plasma model for the diagnostic purpose. Recently, Mar et al. Performed an experiment where they generated a krypton plasma, and in the spectral measurement of krypton plasma they observed the few prominent emission lines of krypton plus ion in this wavelength region. Now we will characterize this krypton plasma using these lines through the detailed collisional radiative model by calculating the electron impact excitation cross sections of krypton plus ion. So this is the energy level diagram of krypton plus ion. This is the ground state of krypton plus, and these are the excited states that we have considered in the present calculation. Krypton plus ion exhibits huge fine structure splitting due to the relativistic effects such as spin orbit interaction and JJ coupling. Any 4s2 NP4 NS excited state has 8 fine structure level, and NP excited state has 21 fine structure level, and any ND excited state has 28 fine structure levels. These are the fine structure levels we have considered in our present calculation. Now, in order to calculate the electron impact excitation cross section, the required transition matrix is given by this expression. In this expression, the phi I and phi F are the bound target ion wave function in the initial state and in the final state. Fi and ff are the distorted wave function of the projectile electron in the initial state and the final state. V is the interaction potential. And now, to calculate the transition matrix, we first calculate the initial and final bound state wave functions. We calculate these wave functions by the GRASP-2K code, and the accuracy of these wave functions is monitored by comparing the excitation energies and oscillatory strength transition probability. In this table, one can see our calculated excitation energies are in good agreement with the available excitation energies, and these are the calculated oscillator strength and transition probability for all the dipole allowed transitions. Now, with the help of calculated wave function, we calculate the transition matrix and obtain the scattering amplitude. This absolute square of the scattering amplitude gives the differential cross section, and the angle integration of differential cross section gives the total cross section. So here's the process how I calculate the electron impact excitation cross section for krypton plus ion. Now I will explain the results for rate coefficient and cross sections. So these are the electron impact excitation cross section and rate coefficient results for the transition from ground state 4p5 to the excited state 4p4 5s excited state. The cross sections are reported with respect to the incident electron energies from its excitation threshold to the 1000 electron volt. The behavior of the cross section curves are known behavior. As the incident electron energy increases, the cross section decreases. The magnitude of the cross section also depends on the nature of the transition, whether the transition is parity allowed transition or parity forbidden transition. This this particular excitation is parity allowed excitation, because the initial state, that is the ground state, has odd parity, while the first excited state has even parity. So this is the parity allowed transition. In this parity allowed transition, there are few transitions which are dipole allowed and few transitions are dipole forbidden transition. The magnitude of the dipole allowed transitions the magnitude of the cross sections of dipole allowed transitions are higher as compared to the dipole forbidden transitions. And these are the rate coefficient results with respect to the electron temperature, and this is again the well-known behavior of the rate coefficient. Initially, as the temperature increases, the rate coefficient increases, and then it becomes a constant. In a similar way, we calculate the electron impact excitation cross section and rate coefficient for the transition from ground state to the 4p4 6s excited state. Here one can see the behavior of the cross section curves and rate coefficient curves are similar as we observed in the excitation of 4p5 to the 4p4 5s excited state. Here, these are the results for the transition from 4p5 and to the 4p4 5p excited state. Here, one can see the magnitude of the cross section curves falls rapidly as the incident electron energy increases. This is because this is the parity forbidden transition, and in this, because both the ground and excited state have the same parity, that is odd parity, and in this type of transition, the cross section decreases very fast as the incident electron energy increases. And this excitation has 21 fine structure transitions. So these are the results for these excitations.
Yeah,
And
finish with 2 minutes within.
okay, and these are the results for the excitation from ground state to the 4p4 6p excited state, and these are the results for the excitation from ground state to the 4p4 4d excited state. These are the rate coefficient results, and these are the cross section results from ground state to the 4p4 5d excited state. So with this cross section and rate coefficient results, we will develop a collisional radiative model for the krypton plus ion. We have also studied the linear polarization for the dipole allowed transitions, and by these linear polarization expression we calculate the linear polarization, and these are the results for the linear polarization, and we calculate the linear polarization with respect to the incident electron energy, and initially the linear polarization increases with the incident electron energy, and at a particular energy it becomes maximum, and after that it decreases and it becomes negative. So these are the results for the polarization, and these are the polarization results when the excited state 4p4 6s and 4p4 5d decay to the ground state. In a summary, so in this work we have calculated the excitation energy oscillator strength transition probability from the Graf-Stuke code, and obtained the electron impact excitation cross section and corresponding excitation rate coefficient for the 116 transitions from the ground state using the relativistic distorted wave method, and using the and obtained the linear polarization using the calculated magnetic sublevel cross section. Now with the help of these cross sections, we will characterize the krypton plasma using the measurement of Marr et al. And develop a detailed collisional radiative model, and obtain the electron temperature and electron density. This work we published in JQSRT, and one can, for the more detailed information, one can see this paper. And for this work, I would like to acknowledge Professor Rajesh Srivastava, and thank you.
Professor Bose. Professor Bose.
Yes.
Professor Bose, there is another presentation by Shalu Jain. It was missed in basically in schedule. So she will finish in 10 minutes. So Shalu Jain.
Yes, sir.
Please finish your presentation in 10 minutes. Okay.
Okay, sir.
Okay.
Yeah, please start.
Sir, were you able to see me or the slide?
Yes, slide is visible. You please start.
Okay. Good noon, everyone. This is Shalu Jain. Firstly, would like to thank the organizer of this presentation. I would like to thank the organizer of this conference for making a part of it. I am grateful to you for giving me the opportunity to present my work before you. Let's make a start. In today's presentation, I am planning to discuss about the theoretical study of the energy and luminosity of an ion beam accelerated in the radiation pressure dominant region under the kind supervision of Professor N.K. Jaman. Let's make a start. My presentation is divided into these sections. My first point will be about an abstract. Then I will introduce the basic concept behind my title. At next, I will be going to talk about the equation of motion of thin plasma foil. And then I will discuss about my relevant results. At last, I will conclude my findings. The purpose of this presentation is to study about the interaction of ultra-intense laser pulse with a thin dense plasma foil, which is of fundamental importance of different fields such as ion acceleration, high frequency radiation sources in medical application and in relativistic astrophysics and so on. For this, we consider the interaction of ultra-short, ultra-intense laser with the ultra-thin plasma layer, and in this reference, we evaluate the energy and luminosity of ions and their dependence on parameters of laser and target, and results are also presented for the different shapes of the target Here I have taken the Gaussian shaped foil target and flat target. The effect of polarization has also been studied and the results will be shown. I would like now to begin the underlying concept of the acceleration of ion, the radiation pressure dominant resin. At the laser intensities of the order of 10 to the power 19 to 23 watt per centimeter square, the radiation pressure of the incident electromagnetic wave starts to play a key role in the interaction of EM wave with ultra thin foil. To define the importance of radiation pressure dominant acceleration resin, let us consider an ultra thin dense foil made up of electrons and ions. It is irradiated by a laser pulse. Due to the high radiation pressure of the laser pulse, electrons are quickly accelerated up to the speed of light, and the ions remains immobile due to their heavier mass. So a strong charge separation electric field is created inside the plasma, which pulls the ion in the forward direction with almost the same speed as that of electron, that is the speed of light. Thus ions got acceleration in this regime where the radiation pressure is dominant. So this regime is very effective regime for ion acceleration. This is the process of ion acceleration which I have told you. And in this course of laser matter interaction, the frequency of the reflected radiation is downshifted by a factor of 1 over 4 gamma square. For gamma is very greater than 1, that is it is an ultra relativistic limit. Here gamma is the corresponding relativistic Lorentz factor, and the energy transfer to the mirror can be estimated as 1 minus 1 over 4 gamma square times of EL, where EL is the energy of laser pulse. Now let's move on to the equation of motion of the thin dense plasma foil. It is the equation of motion of thin dense plasma foil, where beta is the velocity of the foil, gamma is the Lorentz factor, EL psi is the laser electric field, Ne is the plasma density, L is the foil thickness, Mi is the ion mass, and C is the speed of light. And one can solve this equation analytically for the initial condition, that is initially at t equals to 0, our foil is at rest, so beta 0 equals to 0, and assuming total reflection, that is it is equals to 1. Sorry. Then I have obtained the solution for this equation and analytically, and I got this expression. Here W is the 2FL over NEL, and FL is equals to integration 0 to infinity EL psi square over 4 pi. It represents the fluence of the laser beam. Fluence is just about just the incident laser energy per unit area. Let's look at the effect of the target deformation, in which we have used a target with the Gaussian distribution, Gaussian thickness distribution, as L equals to maximum of L1 comma L0 exponential minus R square over sigma t square times raised to the power m. Here L1, L0, sigma t, m, these are the shape parameters, and in this figure the L0 and L1 values are shown, and for L0 equals to L1 value, our shaped foil target converts into the flat target, and the layout of both the targets may be differentiated by taking different sets of L0 and L1 values. At the screen you will see the vector potential of the electromagnetic wave of the frequency omega, which is generally mathematically represented as this equation. Here epsilon is the ellipticity which ranges from 0 to 1, and as we all know, the linearly polarized wave corresponds to epsilon equals to 0, and epsilon equals to 1 corresponds to circularly polarized wave. And one can easily obtain mathematically by simple mathematical calculation. We have obtained the electric field associated with the incident laser pulse or incident EM wave. Now the equation of motion gets reduced in the case of polarization, is where E0 is the peak value of the laser electric field. Now, in addition to the requirement of obtaining the maximum ion energy for high energy physics application, we come to include an important parameter such as luminosity of an ion beam, which is mathematically expressed as this, where F is the laser repetition rate and total is the total number of ions which are to be accelerated. Sigma is the transfer size of the beam. As we can see, the luminosity can be increased by increasing the laser repetition rate, by increasing the total number of ions, and by decreasing the transfer size of the beam. And the decrement of the transfer size of the beam, it can be achieved by the focusing the particle beam into a focal spot, or by irradiating the foil with an appropriately modulated pulse. To obtain the numerical results, we have chosen the following set of parameters. I have taken the intensity of the order of 10 is about 22 watt per centimeter square, laser pulse duration 50 femtosecond, focal spot radius 10 micrometer, laser wavelength 1 micrometer, transfer size of the laser beam 10 lambda. The plasma density is to be Ne is equals to 169 NCR, where NCR is the critical plasma density. And one more important thing, for a Gaussian shaped foil target, we have taken these parameters, which are the shape parameters. And for the flat target, we just set L0 equals to L1 and the other parameters remain same. And this is the...
Shalu, conclude in 2 minutes, okay?
Yeah, 2 minutes.
Okay.
Please.
Let's have a look at the graphics, which we have made a use of MATLAB software to obtain them. We have shown the normal variation of normalized energy and the luminosity with the normalized time for 3 reasons. First point is the result for the different shapes of the target, and we got that the Gaussian shaped foil target is more efficient in transferring the energy and momentum to the ion in comparison to the flat target. And the result is for the polarization. The CP laser pulse is more efficient compared to the linearly polarized wave, and for fixed value of time, we get the energy of ions is approximately 198 MeV in case of CP and 188 MeV in case of LP, and the corresponding luminosity is found in the order of 10 to the power 35 per centimeter square per second. And these are the results for the energy and luminosity for different target foil thickness, which are comparable with the laser wavelength. And these are the results. And for these values, we have obtained the 367 MeV, 300 MeV, or 250 MeV correspond to these values, and the corresponding luminosity is found in the order of 10 to the power 34 per centimeter square per second. So finally, I would like to conclude my findings that when the laser pearl irradiates on the Gaussian shaped foil target, the energy of ions is more in the case in comparison to the flat target, and same as for the luminosity. And if we saw our results, we found that at T approximately 133 femtosecond, the maximum energy achieved by the ion is estimated to be 0.75 GeV, which is nearly close to the Chen simulation results as illustrated in this paper and part B of the figure 1. For the target composed of electron and ion, the CP laser pulse is best in comparison to the linearly polarized pulse. And the last result is when we increase the foil thickness, value of the foil thickness, then we got the energy of the accelerated ion as small as much, and the maximum energy obtained by the ion is approximately 367 MeV, corresponding to L less than lambda, and this value diminishes gradually when the thickness rises and reaches approximately 250 MeV for L greater than lambda. And I would like to thank the organizer of this conference and my supervisor, Professor N.K. Jaman sir, and my advisor, Professor K.P. Maheshwari, and I would also thank my colleague, Mr. K.K. Soni, for the helping hands. Thank you for your
Thank
attention.
you very much, Ms. Shalu Jain.
Yes.
Okay, now the
So
session is over. I think
it's time to thank you, Professor Bose, for doing excellent job and chairing this session. So it is a pleasure that you are having us. And please join the session 4 also. And now there is a poster discussion session. So I request to all the participants to please keep on your video so that everybody can see you and can take pictures. So I am handing over this poster session to Dr. P.K. Sharma. He is from Barkatullah University, Bhopal, and he is a well-known plasma physicist. So I would like to invite Dr. P.K. Sharma to chair this poster discussion session and for further proceedings.
Very good afternoon and heartily welcome to this wonderful galaxy of scientists, researchers, physicists, and all the dear participants who have come together 4 days poster session. I, Dr. P.K. Sharma from UIT Barkatullah University, Bhopal. I am highly obliged and privileged to be a part of this international conference. I thank Dr. Prajapati, the convener of this conference, to give me the responsibility to chair this poster session. We have received a total of 58 research papers in the form of posters in the different categories, and queries related to these posters were welcomed. Now I would request respective authors of the posters to please respond to the queries. To begin, the first question related with BP poster number BP10, the linear dispersion characteristic and shock fronts of EAW in semi-classical plasma. Mithika Ghosh, this is a poster of Mithika Ghosh, and the queries for Pralay Kumar. There is no reference why. Mr. Pralay Kumar asks, there is no reference why. Mithika Ghosh, are you present? Are you listening me? Mithika Ghosh, I think.
Okay, you go ahead, sir. If she is not present, I will note it.
Okay. So the second question related with poster SA01, nonlinear waves in multi-ion cometry plasma with kappa described electrons. And this poster of Sijo Sebastian. And the question asked by the Pralay Kumar, why are the references not put? What are the sources references? What are the basic governing equations? Sijo, can you hear me? Are you present? I think.
Who is the presenting author?
Sijo Sebastian.
Sijo Sebastian. Sijo Sebastian is there. Okay, he is not there, I think. So you can go ahead.
So next question related with poster DP08, molecular dynamics simulation of Kelvin-Helmholtz instability in dusty plasma layers with different velocities and densities. And this poster of Mr. Prajapati and Vivash. Yes, and question asked by Pratiksha, how do you ensure thermal equilibrium? The first question.
To ensure thermal equilibrium, we check the variation of kinetic energy, potential energy, and total energies. And we check what are the variation. If the variation is very small or nearly constant, then we take the that energy as minimum energy, and we can continue with that energy. Thus, we check the constancy of the simulation.
Pratiksha, are you here? Are you satisfied?
Yes, sir. Yes, sir. Yes, sir. Actually, I have already received. I have received his message today morning only. I have got his message, and he has very clearly explained to me about the implementation of News-Hoover thermostat. Also, he has very clearly explained. So I have already gone through that, and now also again.
Okay. Thank you, Pratiksha, and thank you, Prajapati ji. And the next question related with poster BP07, effect of dust concentration of the characteristic of Rugg waves in dusty plasma with Maximilian negative ions. And this poster presenter are K. Shasharia, K. Saharia, and Raj Kamal Kokati.
Dr. Saharia is here, so we can answer.
So the question is, please differentiate between dusty plasma and dust in plasma. question asked by Sachin Kothekar. So, Saharia, are you hear me?
Dr. Saria, please unmute yourself first.
I think
No, he is
I'm
here.
not getting any response. So, the next question related with
Dr. Saria, can you hear us? Please unmute yourself first. We are not able to listen you.
Okay.
Yes, try to answer the question, please.
It's a fluid element only. Here we have took the dust as a fluid element only, not as a dusty dust ion acoustic wave. So it's the ion fluid. Dust acoustic ion fluid. Fluid element is dust that way.
Mr. Sachin, are you present?
Yes, sir.
Are you satisfied?
Okay, sir.
Okay,
Fine.
okay. Thank you. And the next question related with poster BP13, a collisional relative model for the diagnostic of ArCO2 mixture plasma. Yeah, this poster author is Neelam Shukla.
Yes, sir.
And her question is, please comment on the difference in the title of poster and title of postal represented on the conference poster site. Sachin Kothekar asked this question. Sachin?
Yes, sir.
Please.
Please ask what is your specific question.
Yeah.
Dr. Sachin, please ask what is your specific question.
Sir, my question is that as I go through the poster of the candidate, the title of the poster is somewhat different than the title which has been put on the website. That's why the query is.
Let me clear it. Actually,
Yeah.
she may be sent a request to revise this abstract. So unfortunately, we could not update the list. So if you have any other query or question, you can ask.
No, sir. Thank you. Thanks.
Okay, thank you.
Okay. And next question also asked by Sachin Kothekar to Alok Kumar Chaudhary, related with poster BP05, energy generation using nuclear fusion. Sachin asked, what is the role of country India in this ITER project? Alok Chaudhary.
Yes, sir.
Yes, please.
Yes, sir. Sir, India's contribution is very huge in this project. So basically, I can tell that 9% contribution in this project of India, and various components are manufacturing by India and installation advanced Marcel, sir. So cryostat, shielding and cooling system and power generation system. This like component are manufactured by India and also being installed here. Recently, cryostat installed there. So various contribution of India in this project, and definitely it will also help India for the energy crisis. So this is my answer, sir.
Thank you. Are you satisfied? Sachin?
Yes, sir. Definitely.
Okay. The next question related with paper poster BP01, the numerical studies of dissipative instabilities and Hall's plasma. And Sumek, the author is Sukhmander Singh.
Sukhmander Singh from Rajasthan.
And the question asked by RP Prajapati, and the question is, there is no any instability term. Sukhmander, are you here?
Yes. Hello.
Please give.
Yes, sir. I respond to the answer. Yeah, because there is some collision term in the plasma, and this term is in the momentum equation, and the collision frequency get coupled with the electron is closed drift in the presence of collisions. So the collision term is main responsible for the instability.
Okay, so it is a drift kind of instability.
Yeah, it could be said that it is drift instability. Yeah.
Okay, in a Hall cluster plasma.
Yes, yes, sir.
Okay, okay, thank you.
Another second question is, which factor is producing instability in your case?
Yeah, collision frequency.
Okay, okay.
It is answered. Yeah.
Okay, okay, okay. Prajapati ji, are you satisfied?
I am fully satisfied, sir.
Okay, okay. Sir, the next question related with poster as SA14, non-linear evolution of 3D kinetic Alfvén waves in the presence of background density fluctuations. Anu Garg, the poster of Anu Garg. Anju Garg, sorry, Anju Garg. And question asked by Kriti. And the question is, what do the localized structure look like? They look isotropic from the figure, but Alfvén turbulence should produce strong anisotropy.
This is not due to the Alfvén wave, this is due to the kinetic Alfvén wave, which is dispersive in nature. This is 3D propagating kinetic Alfvén wave, not Alfvén wave.
Okay, okay, okay. And the next question, the spectrum of Ka is expected to be close to 8/3, minus 8/3. Are you getting that or something else?
No, sir, this should be close to the Kolmogorov scaling in the inertial range, and which is near to minus, this scaling index is minus 5/3. And after that, there is in the steeper scaling or after the inertial range, there is no till now no observational fact. But they said from the observations that energy is distributed among the different wave number. The scaling is minus 5/3, not minus 8/3. Or it varies from region to region. In Corona, this is minus 5/3.
Thank you, thank you. Okay. And the last question asked by Dinesh Rathore, VIT Chennai, to R core, and the title of this paper is terahertz radiation propagation through double layered metallic plasmonic waveguide. R core. R core, are you hear me?
I think
the question is, what is the propagation length getting in the metal air interface waveguide of SPP? R core, S core,
Rupinder
E Kumar.
Rupinder Kaur, I think she is present here. Dr. Rupinder Kaur. No, she is not responding. So I have two questions also, sir. Regarding the poster BP02 by Shahida Parveen, and the question is asked by Professor NPS Seni. The question is, how does superthermality play its role in physical context or changing characteristics of kinetic solitons? So, Shahida, please answer.
Thank you very much. Am I audible?
Yes, yes, you are audible.
Actually, kappa means the electrons are the other species are energetic particles. So the energetic particles mean they have more energy, and the energy is related to the amplitude of the solitons. So they make when the particles, we take the kappa distributions, the particles become energetic and their amplitude, the amplitude of solitons is increased, which make the coherent structure, I mean solitons become narrow, and the amplitudes is increased.
Okay, I hope Professor Seni will be satisfied with your reply. And we have last question of this session. It is related with the poster BP07 presented by Dr. K. Saharia. And the question again asked by NPS Seni, that how large are rock wave in comparison to KDV solitons?
It's about 3 times. No, it's about 3 times we have observed. Or observed one is around 3 days. It's hard to only, but if it is super rogue wave, then it may be 5 times also compared to the carrier wave.
Okay. Okay, so thank you all. And see, these posters are available on the website. So everybody later you can see the posters and you can comment. So the concerned presenting author will respond to you. So it will be open for the next week also. So anytime you can watch the poster. There are so many beautiful posters are there, and really the participants, they did a very good job. So I thank you all again. And please, Dr. Sharma sir, conclude this session so that we go for lunch and come again at 2:30. There are nice
Thank you.
talks of laser plasma injections.
Thank you, Pratap ji.
Thank you, sir.
Okay, so thank you all. We will meet at 2:30 again in the last session of this conference. Okay, see you all again. Bye.
Okay, sir. Thank you.